All right, welcome everyone to week, we'll call it 6.5/7 of our reviews. This would be our 7th week of the semester if not for the storm, so we're just going to call it 7. I have a brief correction from something I told you all last week. I mistakenly said for rapid equilibrium, K2 is significantly greater than K-1. I had that backwards. K-1 is significantly greater than K2. And we're going to see a practice problem for that down below. Otherwise, I would be drawing this out on the screen. But I apologize for that. My notes got out of order and I just got very confused, so I apologize. So last week I also introduced, or I think your professors probably beat me to it, but we talked about inhibitors last week. And when we talked about inhibitors, we talked about how your Vmax and your Km will change with an inhibitor. So for example, when we talked about competitive inhibitors, and with this formula, which I hope you all aren't tired of this formula yet. I love it still. When a competitive inhibitor binds to the enzyme, that decreases this and thus decreases the affinity of the enzyme for its substrate. And so we said Km will increase, right? But the reality is Km is intrinsic to the enzyme. Km is the affinity of the enzyme for its substrate, and that does not change, okay? So the answer to this is kind of, but the real answer is no. And the reason it's no, and I'm sure you guys can see the table down below. I didn't want to space it out too much because there's not a ton to write here. This table calls it apparent Km and apparent Vmax. Because Vmax and Km are, like I said, they are intrinsic to that enzyme. That is something that, like, if I had an enzyme in my hand, or like a bottle of this enzyme, I could write on that bottle, the Km for this reaction catalyzed by this enzyme is this, the Vmax for this reaction is this. It doesn't matter what solution you're in, it doesn't matter any of that. So what inhibitors do is they affect the apparent Km, okay? So as you all can see here, Km can be changed depending on the reaction. So obviously if there's no competitor, apparent Km is equal to Km. But when you have a competitive inhibitor, I told you all that Km increases. The reality is that the apparent Km increases by this kind of, excuse me, I think I need to draw that so slanted, by this, one more time, by this factor. All right, and you see this factor kind of popping up in every single inhibitor with the exception of the mixed, and we're going to talk about the mixed in a little bit. But this is 1 plus the concentration of the inhibitor over Ki. And Ki, just like every other capital K that we've been dealing with, is kind of an affinity. It's kind of the, there's my mouse, okay. So Ki, excuse me, Ki is equal to the affinity of the enzyme for the inhibitor, okay? In other words, this affects how effective the inhibitor is. So if you have a very, very high Ki, you need a very, very high concentration of inhibitor to kind of make up for that. If you have a very, very low Ki, you need a low concentration of inhibitor to make up for that. And I think that that's especially obvious given that relationship right here, right? It's concentration over affinity, excuse me, over the inverse of affinity, I should say, right? Kind of like Km is backwards, Ki is similar. So I told you all we'll talk about mixed later. And the reason is, like we said, mixed is a little bit beyond Biochem 1 at an undergraduate level. If you're taking it at a graduate level, you might have to deal with it. If you're taking a really advanced biochem course, you might have to deal with it. But for this class, mixed inhibitors are a little too complex, and this is why. This alpha factor right here is kind of what screws up mixed inhibitors. And the reason is, when we talked Lineweaver-Burke plots last week, we talked about how actually I can just pull up the graph, how a pure non-competitive inhibitor would look like this, the very bottom one, right? So let me draw that here real quick. There it is. All right. But when you have a mixed inhibitor will, there we go, will have a different Km, a different Vmax, and a different slope. And so while before we could say this will be the same for both, well, a mixed inhibitor could look like that, or it could look like that, or it could look like that, whatever. There's nothing that indicates what a mixed inhibitor is beyond that it's just very, very different. And so it just really complicates things because of that alpha factor. Okay, so that's kind of the conclusion of inhibitors that I didn't have a chance to go over last week. And now we're going to jump into the material that I believe you all covered both last Thursday and yesterday. And that is kind of the types of reactions that we're dealing with. So first are single displacement reactions. And I'm going to kind of zoom out as much as I can because there are two kinds of single displacement reaction. There is the first one that you see, and there is the second one that you see. So these are different, or I guess I should start off by saying single displacement reactions are called sequential reactions. All right? Sequential. And the reason they're called sequential is regardless of what we look at. A and the enzyme bind, and then B and the enzyme bind, and then products, like the products form. And I should mention Q is just another product. And then one of the products falls off, and then the other product falls off. They happen in sequence, okay? And when we look down below, very similar thing. A joins, then B joins, then we get the products, then Q leaves, then P leaves, right? They're very sequential reactions. However, even with that sequentialness of them, you can have a random single displacement reaction, or you can have an ordered single displacement reaction, right? So the random single displacement reaction is random in the sense that A or B can bind first or second. So if A binds first, you get this AE. If B binds first, you get this BE, right? And then regardless of which binds first, they come together for this, and you guys know I love highlighting, so this reaction has to happen, right? And then just like they can bind in any order, the products can also be released in any order. So Q could be kicked off first, or P could be kicked off first. Doesn't really matter, and that's what makes it random, okay? Ordered, on the other hand, is exactly as it sounds. It's ordered. A has to bind in order for B to bind, and then Q has to leave in order for P to leave. So the way that I like to think about the random single displacement reactions is if you have an enzyme with two active sites that interact somehow. So this isn't the best example because I drew this a little too far away, but if these were really, really close together, then you could have A over here and B over here, and they might have some interaction with one another, okay? And so because the active sites are kind of separate, you can totally just have either bind in any order. With ordered, I like to think of it as one active site opens another, or one active site creates the other. So I would think of my enzyme like that almost, and then A has to fit in like this in order for B to fit in like this, right? And then when B is turned into Q, B has to fall off first in order for A, which has become P, to fall off, right? So that's how I like to think of it. I don't know if that helps at all, but that's my kind of way of thinking about this, all right? So let's talk about what it looks like. So this slope is ugly. I'm not going to talk about it. You don't need to know. The reason that we talk about this is because the trend resembles an uncompetitive inhibitor, or I'm sorry, a non-competitive inhibitor. I apologize. So the reason that it resembles this non-competitive inhibitor, because exactly like these arrows show, as we increase, I'll keep it blue. As we increase our concentration of B, our slope decreases, okay? And that's the second substrate. And actually, I just want to make sure I explain both of these, whether they're random or ordered, take on this kind of this shape. And so, okay, yes, sorry. So this point where they meet is A, effectively, or it's the -1 over the inverse of A, of Ka. But yeah, so this is a test question that I've seen somewhat regularly, is like, what kind of reaction will resemble a non-competitive inhibitor, or what kind of reaction has this graph, and they'll show a graph, and they'll increase the concentration of a substrate, and this trend will follow, okay? And that's single displacement reactions, right? But there's also double displacement reactions. All right, so double displacement reactions, or I guess I should say, the single displacement reactions, we've been talking about sequential, right? One binds, then the other binds, then you have that middle step, then everything falls off, whether it's in one order or no order or whatever. Double displacement are the ones that your professors might have called ping pong reactions. And I always love hearing that, because it's weird to think of a professor like a PhD with, you know, a ton of experience calling a reaction ping pong. It's weird to me, but the reason that it's a ping pong reaction is effectively A has to finish completely before B can touch this enzyme, okay? So let's look at, and once again, this is kind of similar in the random and ordered sense, but your enzyme takes on two forms, okay? So when it binds with A, that's fine, nothing changes. But as soon as it binds to A, it can convert A into product P. When it does that, the enzyme itself changes. So it turns into E prime, okay? E prime now can bind to B. It has to be in this configuration. Excuse me, that's too many circles. There we go. It has to be E prime, it can't be E. And then once it's bound to B, it can once again react and convert B into its product Q, okay? And then finally, once it's done that, the enzyme is back to its normal state. Okay, so this is something that I think is kind of weird, but also conceptually it makes sense, right? When the enzyme changes shape, it kind of creates this cycle where it gets ping-ponged around, right? That's why it's called that. So A finishes with it, then B takes it, then A takes it, then B takes it, back and forth, like in a ping pong game. And so double displacement reactions are separate reactions using the same enzyme, okay? I hope that makes sense. If it doesn't, please feel free to ask. Actually, I'll wait a moment because I see someone reconnecting. No? Okay, never mind. All right. So what you see down here is another kind of representation of it. And this is kind of how the ping pong table works, basically, right? So you start with E binds to A reacts, P gets kicked off, and then it repeats over and over again. And it's also in equilibrium. So it could go the other way if we wanted to go this way, right? This over here is another kind of interpretation of the same thing, with A turning into P, basically on this side, with E involved. And then when it does that, it converts it to E prime. E prime goes into here to bind to B, and it helps this conversion, right? So these are just other ways kind of to show the same thing in a diagram. But let's talk graphically. So graphically, this resembles an uncompetitive inhibitor, right? And I want to underline this, uncompetitive, right? So before we were talking non-competitive with single displacement, uncompetitive are double displacement, okay? And this double displacement reaction, once again, test question could be, what kind of reaction will show these lines when I change the concentration of B, right? Or will show this graph when I change the concentration of B. So as we increase the concentration of B, the slope does not change. So let's look back up here. The slope changes as we increase B, it gets steeper. Here, the slope isn't changing at all. What's happening is the slope is affected by A, and we're increasing B, right? In this case, the x-intercepts and y-intercepts are changing, okay? And it's kind of, I think of it as decreasing even though it's really not. It's shifting to the right is what's happening, right? We kind of call it shifting down, but what's really happening is it's shifting to the right because it's getting faster, okay? As 1 over V, so great example, 1 over V is decreasing, which means V max is actually increasing, or V is increasing, I should say. We're not talking V max, I apologize, okay? All right. So that is kind of the introductions to that. And now we can talk about exchange reactions. So exchange reactions are really interesting because they're a great way to tell if what we're dealing with is a single or double displacement reaction. Okay? Excuse me. So the example that most professors use is sucrose phosphorylase and maltose phosphorylase. So I can use that one, and I probably will. I can pull up another one, but I don't know if it'll benefit you as much. So I'd rather walk through the sucrose and maltose phosphorylase reaction. So the reaction of sucrose to phosphate. Sorry, I should write this, shouldn't I? Sucrose plus inorganic phosphate, double arrows, and that gives you glucose 1-phosphate, which I'll be abbreviating G1P, and fructose. Okay. On the other hand, you have maltose plus PI, and it gives you pretty much the same thing. Maltose plus inorganic phosphate, double arrows to G1P plus another glucose. Glucose. There we go. Okay. So if we were to trace the phosphate that we added, the inorganic phosphate, the key here is, actually, all right, so the way exchange reactions work is effectively, we're saying we're going to take this G1P and we're going to add P32 is what they use, just something that you can track, basically. Something you can track. And exactly like the name suggests, it'll exchange and become G1P with these trackable phosphorylases plus regular inorganic phosphate. Okay? So when that happens, we can figure out if it's single or double displacement. Why? Because let's think about, shifting back over here. Let's think about these two in a single or double displacement reaction. If the sucrose phosphorylase enzyme, which catalyzes the first one, were to, let's say, catalyze this reaction, then what that tells us is that sucrose is binding to the enzyme first and creating glucose and fructose. And then that glucose bound to the enzyme is binding to the phosphate, and then that's being released as G1P. Okay? In other words, if, sorry, I keep losing my mouse, there it is. If this is catalyzed, I'm going to rewrite that because I can't even read my writing. So if this reaction is catalyzed, and let's say this reaction, the top reaction, our glucose gives us this. What that tells us is that the glucose had to bind to the phosphate separately from the sucrose, okay? It didn't bind to both at once, all right? In other words, sorry, I'm trying to scroll back up to the diagram. In other words, oh goodness, this could take place because remember that these are in equilibrium. So if we have, and I'm going to try to fill this in, so I'm going to erase this and start labeling it with the stuff from the exchange reaction. Okay, there we go. So if A is sucrose, and then P is G1P, and then B was the inorganic phosphate, and Q is, sorry, hang on, I forgot it, maltose? Fructose, I apologize, fructose. The only way an exchange reaction would work is right here. This has to be present. But when we look at single displacement reactions, that isn't present. Both have to be present in that highlighted equation, that highlighted bit, in order for a reaction to happen. So once we introduce 32p, after the reactions have already taken place, well, the 32p can bind, and sure, we can go that way, but we can also go this way. That radioactive phosphate sorry, I was blinking on the word. That radioactive phosphate can bind to the enzyme and bind to G1P, and it can replace the phosphate in there for the radioactive phosphate. And so that's how we can use an exchange reaction to tell us that, as in the example your professors gave, this first reaction is a double displacement reaction, and the second reaction is a single displacement reaction. Okay? All right. So that is the whole spiel on types of reactions. Now we get to talk about enzymes. And like I mentioned last week, I love enzymes because this is where biochem becomes biochem, and not Gen Chem Part 2, and not, biochem plus ochem, whatever. It's really its own subject, starting with enzymes. So as we know, enzymes increase the rate of reaction by decreasing the activation energy. Okay? So this is uncatalyzed. I drew that poorly, excuse me. This is catalyzed, right? It brings this down significantly to something like this, right? And in doing so, I actually want to get rid of this. And so how does it do that? Okay, so effectively the enzyme will bind the substrate and the transition state. So just a quick reminder, I'm going to draw over on the right side. The transition state, which is kind of, it looks like a little railroad for the symbol, is that top bit right here of the potential energy, the energy diagram, and it's the most unstable state. Okay, so this is something that's a little bit unintuitive to some people. The enzyme binds the transition state more tightly than the substrate. Okay, transition states. I apologize, I keep doing that. Transition states. And the reason they bind transition states more tightly is because this is how they lower the energy. How they lower energy. Okay, so let's think about that. And some professors will include a diagram that shows the enzyme substrate complex with like a significantly low activation energy. But I think that it's just a little bit easier to think of it like this. Okay, when you bind to that transition state, you stabilize the transition state. So the way that I think of it is, if this is reactant A, and then my transition state is really, 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 really negative, and that's why it's so unstable, my enzyme, I apologize, I'm running out of space here, my enzyme is just really, really positive, and so it stabilizes this. It can fit my substrate, can fit the substrate, but it actually serves to stabilize this because it's kind of, I don't want to say it's made for it, but it kind of is, right? Sucrose phosphorylase, like we talked about right above us, is made for the reaction for sucrose. And so because of that, if we want to think of it as Km, because let's tie everything back together. The Km for the transition state is significantly lower than the Km for the substrate. The logic here is that makes this a higher affinity, and thus it really does bring this way down. Okay, it makes it a lot more stable. Okay. So, does the lock and key hypothesis or the induced fit hypothesis favor the formation of the transition state? So we're just going to do a quick recap of of each hypothesis, just very briefly. So the lock and key hypothesis basically states that this enzyme, and I apologize, this is the only shape I can draw consistently. This enzyme is the key, or I'm sorry, the lock, and this substrate, S, fits into that lock perfectly, and so it's the key, right? And so this reacts really easily. The induced fit hypothesis is a little bit different. The induced fit hypothesis basically says something along the lines of the substrate and the enzyme kind of distort. And what I mean by that is, let's draw that shape again. Nope, it doesn't look good. Let's try it again. So something like that. The substrate fits in here, fine, great, and it reacts. But when it reacts, what it does is the transition state now is really, really unstable. And so as a result, the enzyme shifts to kind of wrap around the transition state, like that. And so that's the induced fit model. It stabilizes to a transition state, and then eventually either it'll stay in that old shape or it'll take on, or I'm sorry, it'll stay in that new shape that it made, or it'll take on its old shape again and it'll be back to the product side, right? So the induced fit model is the model that, exactly like it says here, that explains why the transition state is favorable. It's what explains that specificity of the enzyme, because it's basically saying the enzyme adjusts to stabilize the transition state. Whereas the lock and key hypothesis is just kind of saying, if it fits, cool, if not, try again, right? And so it's right here, induced fit, okay? I hope that made sense. If it didn't, please ask, because I know that it's not the most intuitive thing in the world. Okay, all right, so we're gonna shift gears to number 7. Well, not really shift gears. This is still along those same lines. Why are transition state analogs? And by the way, I have seen these on pretty much almost every exam that I've seen, maybe every other. Why are they more effective than competitive inhibitors? Well, let's talk about it. A transition state analog is kind of like the inhibitors that we talked about last week, except rather than binding specifically to the enzyme or the enzyme substrate complex or both or anything like that, transition state analogs are basically competitive inhibitors that resemble the transition state. Exactly like it sounds, right? And so they're more effective than competitive inhibitors, kind of based on what we just talked about in number 6 and 7. And here's why. A competitive inhibitor, let me see if I can draw this again. A competitive inhibitor, if I'd planned this right, I would have done it inhibitors in red, but that's fine. Inhibitors will be in green. Competitive inhibitor takes on the same shape. So if we look between the drawing in number 6 and drawing in number 7, the inhibitor looks basically exactly like the substrate, and so it can take its spot. But in number 5, we established the enzyme binds the transition state more tightly. We said that as a fact. And so it is a fact. And so given that, where did my mouse go? There's my mouse. Given that, a transition state analog is kind of an upgraded competitive inhibitor. So the TSA, if we were to have, for example, the transition state looks like this, maybe, I don't know. The TSA will look like this, and it'll resemble it in more ways than one. So it won't just take on the same shape. Up in number 5, I drew a bunch of negative charges, around my transition state. The same thing can be for my transition state analog. There will be a bunch of negative charges here. So, like we said, if my enzyme is positive, will it be more attracted to? this inhibitor or this transition state analog. And it ends up being the transition state analog. Effectively, they're kind of, in my mind, they're upgraded competitive inhibitors. I don't know if that's the way that you all want to think of it, but that's how I think of it. And an important note is, and this is something really interesting, TSAs are stable. So this transition state is unstable because of its charge. This TSA is stable. So it may not be as charged as a transition state, but the transition state is around very, very temporarily, right? It's so unstable that it wants to move quickly. This transition state isn't. Since it's stable, it can stay bound to the enzyme pretty much indefinitely. Oops, excuse me. So, can bind to enzyme indefinitely. And so because of that, they make really good drugs, they make really good inhibitors, because the enzyme transition state complex is so, has such a high affinity, or I'm sorry, a low Km, so high affinity for each other. And so it really does end up being a better competitive inhibitor effectively. Now, your PowerPoints probably have a couple of drugs, so some of the more famous, or not famous, but some of the ones that most professors end up using are like neuraminidase, statins, Tamiflu, stuff like that. Some professors ask that you know all of them. Some professors ask that you know only like one or two. So I don't want to confuse anyone and explain a bunch about stuff you don't need, or tell you these are the ones you need and ignore some. So I always say for the drugs, I'm going to skip over them so as to not waste anyone's time. And I highly encourage you to double check with your professor if they don't say so during the lecture, which ones they need specifically. Okay? All right. So since we're kind of shifting gears from inhibitors, now we're going to start talking about enzyme catalysis. So just a quick kind of run through. We've talked about in the first few weeks enzyme structure with amino acids. Then we moved on to, then we moved on to kind of other kinds of structure like primary, secondary, tertiary, etc. Then we started talking about inhibitors, so the binding of the enzyme, right? Now we're going to talk about the actual enzyme catalysis. And 4 of these 5 are types of catalysis. And I'm not going to waste our time and not tell you the answer, but we're going to spend some time here to talk about each of these methods. So the answer to this one is C. That's not a type, because let's talk about each of the other 4 now. So catalysis by proximity is also called like the formation of a near attack complex. Okay? And effectively what happens is the enzyme brings the substrate to its active site, and when that collision kind of hits, the active site forms that near attack complex. The forces contact each other, and it forms the bond effectively, right? So I don't like drawing this because it's very precise, but kind of think of it like, I guess, if, I don't know, T, S, C, and then whatever else is in this amino acid, if these 3 are forming the near attack complex, then what they'll do is the rest of this enzyme is basically kind of curling this way to push the substrate in, and the substrate, which I'm going to shift and start doing in green so it makes more sense, will come in at exactly the right angle, to bind right here where it needs to, or something like that, or maybe it wants to bind on this side, whatever the case may be, it binds at that exact angle. And so that's what proximity is about. Proximity is about collisions and angles, basically. Collisions and angles. Okay? Covalent catalysis. Right? So covalent catalysis is, exactly like it sounds like, right? A temporary covalent bond. And that bond is really good for stabilizing. This covalent catalysis, the easiest way to do it is a nucleophilic attack by an amino acid or by the substrate onto the amino acid, and it effectively just attaches them together for a moment to facilitate electron transfer. So there's not a lot of great examples of this in your book, or I'm sorry, in your in your slides and in your book to some extent. Some professors will include them, but the big thing to keep in mind here is covalent catalysis. It's all about a nucleophilic attack, okay? The next one here is general acid-base catalysis. And so this is kind of fairly straightforward, right? It's the transfer of a proton. The proton can either be transferred from the enzyme to the transition state, from the transition state to the enzyme, wherever, right? And so the transfer of that hydrogen can stabilize a group, obviously. It can also be used to activate a nucleophile. So like you guys learned in organic chemistry, alcohols, so that OH group is a terrible leaving group, but if you protonate that and make it OH2 with positive charge, it becomes a great leaving group. And so that that can really help you activate a leaving group, activate destabilize a leaving group so that it leaves, and so to facilitate nucleophilic reactions. You can also transfer that proton in order to improve the interactions within the transition state, basically. So if it, for example, we talked about it stabilizing charged groups, but by transferring that proton, you may end up, for example, protonating whatever arginine or something, and then that arginine can then help have some electrostatic interaction with some other amino acid, and then, you know, kind of ripple effect to stabilize it, whatever. But the basic thing about general acid-base catalysis is proton transfer. Proton transfer. And I just realized I didn't write anything for covalent catalysis, so I'm going to say temporary covalent bond. Covalent bond. Okay. So if you all think back to most of organic chemistry, you'll remember base catalyzed or acid catalyzed reaction. Well, these enzymes basically help with those inside our body. Okay. And then the final type of catalysis is metal ion catalysis. So this is a metal ion. So the common ones in your body that we're going to be talking about especially are iron, magnesium. Those are two that are going to come up later in the semester, but it can also be something like zinc or you know, a bigger thing like osmium or something like that could be used. Most likely not in the body since osmium isn't naturally found in there, but something like that. And the key to metal ions is that they most often exist as cations, right? We talk about iron +2, iron +3, magnesium +2, zinc +2, right? And they're very often in that state because they lose electrons so easily. And so basically these positive charged metals are really helpful for kind of a couple of different things. First is proton transfer transfers a single proton. This is like +2, +3. It's really strong electrostatic interactions, which can be really good for stabilizing structures. It can also help kind of, well, stabilize the charge in general. And then also what's called coordination chemistry, which is the use of basically metal ions binding to organic compounds. It can serve to kind of create a strong nucleophile, basically. And that's kind of less important, so we don't talk about it often, but it is one that is mentioned briefly. Okay. So that's this question. Next, let's talk kind of details about each of these types of catalysis. So there are 3 main amino acids that participate in that general acid-base catalysis. I've only listed one here. Even without knowing anything about this type of catalysis, I hope you all can pick it, the right answer. And the reasoning is valine is nonpolar, alanine is nonpolar, tryptophan is aromatic, and if you remember anything from OChem 2, aromatics are a pain in the butt to deal with. They're not going to lose protons easily. Glutamine is an amine, so I guess it could, but histidine is the one that we know most commonly as a base. So histidine is the right answer here. The other 2 actually, before I go into those, histidine is very, very commonly involved. So like if you had to pick one of the 3, it would most likely be histidine. The other 2, as you might have guessed, are aspartic acid and glutamic acid, right? They're both acids. it's kind of straightforward from there. Yeah. So these three, if you see them, I strongly encourage you to assume general acid-base catalysis. Okay, or one of the three, I should say. Okay. All right. So this question is kind of a review from when we talked last week, but it's also kind of new this week. You talk in more depth about trypsin and chymotrypsin and the rest in this chapter, or I guess through this week's material. We talked about it before. Anyways, so trypsin cleaves on the carbonyl side of either arginine or lysine. So this is the N terminus, this is the C terminus. So I'm just going to look for arginine, which is R, or lysine, which is K. So I see an R right here, an R right here, and a K right here. Oh, yeah, and a K right here. Good. Okay, so we have arginine to proline is the first one. This bond should be cleaved. Arginine to D is aspartate or aspartic acid. I'm going to write aspartate for convenience. Excuse me. And then lysine to L, which is leucine. So these are the three cleavage sites for trypsin, except there's not. This only gives us 2 fragments rather than the 3. So why is that? So when we look at this, the key to remember here is if something is cleaving at the carbonyl side, that means it's probably affecting the peptide bond itself, right? So when I look at the peptide bond, just a quick reminder, so this is the central carbon, R1, then we're going to go nitrogen, and then carbon, R2, etc., right? I don't want to waste our time drawing too much. So it's most likely affecting this area right here if it's going to cleave at the carbonyl side, or obviously if it's the N-terminal side of R2. So let's look at how this area could be affected in any of these. So I guess I'll just give it away. So proline, if you guys remember, is that weird one where this is kind of part of this R group. Like this would be the hydrogen. This is the R group of the proline molecule. And so because of that, trypsin cannot cleave proline, or trypsin cannot cleave an amino acid followed by proline, right? In this case, it's answer choice E, right? It cannot cleave when the amino acid is followed by proline. It doesn't matter whether you have a base, an acid, something nonpolar, something close to the N terminus or C terminus. Trypsin can cleave all of that. It cannot cleave when you have a proline following it. Okay, that question comes up not regularly, but it's really good to kind of keep that in mind for other cleavages, for other proteins. Okay, right. So catalytic triad. So serine proteases come up quite a lot. And they're kind of famous, I guess. They're a really, really common type of protease, and they kind of show a mixture of covalent and acid-base catalysis, and they do this using 3 enzymes. Okay, I don't know if anyone knows those enzymes, but we're going to kind of cover the mechanism briefly, and then we're going to talk about it. We're going to talk about the specific amino acids that are used. So the first thing is you have 2 amino acids, so A1, A2, A3. This is the catalytic triad. 2 of them are basically there for I should say the first is there to help form low barrier hydrogen bonds, which I very briefly skim over because there's not a ton of questions on them, even though they are absolutely important. But effectively what happens is it forms that low barrier hydrogen bond to allow for easier catalysis, or I should say easier proton transfer. So the first step is facilitate proton transfer. The second step is I don't know why I drew 3 there. I apologize. The second step is that proton, or that kind of like setting things up with that low barrier hydrogen bond. Now let's just do the actual proton transfer. And then third, I told you all that it's kind of a combination between general acid base and covalent. Well, covalent catalysis is generally formed by nucleophilic attack. And that's exactly what we see here. Okay. So looking at, oops, there we go, wrong way. So looking at the 4 amino acids here, I told y'all histidine is the #1 thing present for general acid base. That's true in this case. Histidine is the thing that does the proton transfer. Cool. Okay. So threonine, I remember, has an OH group, and so does serine. So they would probably do one thing and the other one is wrong, which leaves aspartate being correct. And in fact, it is. Aspartate helps facilitate this proton transfer because it's got a pKa and it's got a very low pKa, but its pKa is actually around 4. And the reason that that's important is protonated histidine also has a pKa around 4, or I should say, I'm sorry, a pH around 4. Okay, all right. And so they help each other transfer things. Serine is the thing that does the nucleophilic attack. There we go. And threonine is not. Okay. So this chapter is very technical. I talk about a lot of like kind of other catalytic triads, but effectively catalytic triads are 3 steps. First, the acid orients and stabilizes the base. Second, the base polarizes the nucleophile. Third, the nucleophile attacks the substrate. Okay, these 3 are the big catalytic triad kind of like thing to remember. Okay. We talked about a couple of other things like aspartic proteases and a couple of kind of random unique ones, but this is the bulk of the chapter and the bulk of the questions that you can be asked on this exam. I want to shift gears now though, because I know your exam is tomorrow. I picked a couple of questions from what I think are the most commonly asked types of questions that you should absolutely expect tomorrow that I want us to work through. Before I do, I want to ask, does anyone have any questions? So that I have time to cover those if there are any. Okay. All right, so seeing no questions, I'm going to go ahead and just start working through these problems. So question 12 is an ESI mass spectrometry question. This 2 peaks emerged is partly because I always forget to write 2 neighboring peaks, but these are neighboring peaks. I apologize. And those are their M to Z ratios. So just a reminder, when we set this up, we do M over Z equals the smaller number. And then M, sorry, I apologize, that was not correct. M plus Z over Z is the smaller number, excuse me. In this case, it's that 842. And then M plus Z plus 1 over Z plus 1 equals that 912.3 number. However, we're not going to do it that way. We're going to use the formula that I showed you guys earlier, which is y minus 1 over x minus y is equal to z, right? Much easier. So in this case, just a reminder, x is the larger number, y is the smaller number. So we're going to take 842.7 minus 1 over 912.3 minus 842.7. And normally I would actually do this the long way, so I actually don't have the setup for this one, so give me one moment. The top is obviously 841.7. 912.3 minus 842.7 is 69.6. None of that was right. I miswrote that. I apologize. 69.6. There we go. 69.6 gives us the answer of 12.09. And like I talked to you guys about earlier, this is effectively a charge of plus 12. However, this is just Z, right? So just a reminder, the charge on this protein at 842.7 is plus 12, but the charge on the protein at, or no, do I have that backwards? I think I have this backwards. I do have this. Yes, so I wrote this wrong. These should be flipped. My apologies. This is the larger number, 912.3 and 842.7. So as a result, Z is the charge on this, and so the charge here is plus 12, the charge here is plus 13. So be careful of what the question is asking you for. If it says, what is the charge on this protein at peak, blah, 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 sure, okay. And just to make sure you all know how to do it the long way, just in case you do need it, I'm going to work through that really quickly. I hope you don't have to use this way, but just in case. And yeah, okay. So Z plus 1 equals 842.7. So we multiply over M plus Z equals 912.3 Z, subtract 1 from each side. M equals 911.3 Z. Same thing is going to happen here, except it's going to end up being M equals 841.7 times M plus, or I'm sorry, Z plus 1. Set the masses equal to each other. 911.3 Z equals, and I'm going to go ahead and distribute, 841.7 Z plus 841.7, subtract from both sides, and actually what you end up getting is 69.6 times Z is equal to 841.7, which is exactly what we have here. So we know that the answer is going to end up being 12.09. Okay. I apologize that I went very quickly on that one. I didn't want to waste your time if you already know it, if you don't need it. I just thought I'd do it just to be safe. And we can review that if you need, either drop in at tutoring or just ask now. And then finally, what is the mass? I'm just going to take this one and bring it down. So M plus 12 over 12 equals 912.3. I'm just going to very quickly multiply that by 12 and then subtract 12, and you get 10.9 kilodalton effectively. 10.9 kDa. Okay, and that's that. All right, next is how long is an alpha helix with 5 turns? So the previous problem was basically just this is what you're going to end up getting. This one is more secondary structure in general. You can get, excuse me, you can get alpha helices, you can get beta sheets, you can get parallel or anti-parallel beta sheets. So just in general, secondary structure is going to be on this exam in some way. So the numbers that I remember for alpha helices are 3.6 residues per turn and 5.4 angstroms per turn. So in this case, since we have 5 turns, it's going to be, the train tracks are really easy, 5 turns. These cancel and you multiply. The number we end up getting is 5.4 times 5 is 27. So the answer to this is 27 angstroms, which means that it is D. And if I said D, I would get it wrong. Okay, D is not the answer. Keep track of your units very carefully. They love to trick you on this. This is in angstroms, so to convert to nanometers, multiply or divide by 10, and the answer ends up being C. Okay. Units. I cannot tell you all how many I've missed because I was doing it in angstroms and the answer is in nanometers or vice versa. Okay, so just keep track of that. And also, let's solve how many amino acids this would include. Would be kind of similar. It would be 3.6 residues per 1 turn. Oops. Oh, excuse me. Try that again. There we go. And then we're going to multiply that by the 5 turns, and we get 18 residues. Okay? All right. So this is the type of question that I accidentally gave you the wrong information for last time. So we're just going to work through it one more time. So what it's asking, or I should say, it's giving us that it follows Michaelis-Menten kinetics, which is great. Excuse me. It tells us the values for the various Ks, and then it says at what substrate concentration will the initial velocity equal 1/2 Vmax. So, excuse me. So just a reminder that this, let me grab my highlighter. There we go. This is the definition of Km. Okay. I would love it if everyone had that memorized. If you don't, you can always derive it. Just remember. Okay. And the way that you're going to go about deriving it is starting from that Michaelis-Menten equation. So if you have, so V0, or just V at some point, is equal to Vmax times the substrate concentration over Km plus substrate concentration. We're going to say V0 is 1/2 Vmax. And then the right side ends up being the same, so I'm actually not going to write it out. I'm going to say these two equal each other, divide Vmax from both sides, and you get that 1/2 is equal to substrate concentration over Km plus substrate concentration. Excuse me. From here, I personally like to flip both sides. I think that it's just a little bit easier. So I say 2 is equal to Km plus substrate over the substrate, and then multiply substrate concentration equals Km plus S, subtract S from both sides, and you get that the substrate concentration is equal to Km. Okay, now let's actually solve for Km, right? So Km, I hope you all remember, is going back to the formula, and I'm going to just quickly go to last week's real quick. It's all the ways to get rid of the enzyme substrate complex divided by all the ways to form the enzyme substrate complex. Okay, oh, I didn't realize this would bring me all the way back up here. I apologize. Okay, there we go. So Km is equal to K-1 plus K2 over K1, right? So in other words, if we, I guess I'll do it up here. Enzyme plus substrate to the enzyme substrate complex, and that goes to enzyme plus product. If this is K1, K-1, and K2, you have K-1 and K2 on one side because they're effectively the arrows pointing away from the complex. And then you have, I'll do it in green, K1 on the other side since it's pointing toward the enzyme substrate complex. And then we're going to plug in our numbers. And so K1 is 6.5 times 10 to the 8th. K-1 is 4.5 times 10 to the 5th, and 3.7 times 10 squared. 4.5 times 10 to the 5th plus 3.7 times 10 to the 2nd. Okay? You're going to plug in all your numbers, you're going to get a value out of this. Excuse me. The value ends up being 6.93 times 10 to the -4th. Okay? 6.93 times 10 to the -4th. And that ends up being your Km value, and also the concentration of substrate at which initial velocity equals half of Vmax. Okay? Yeah, okay. So, all right. So the next question is a very, very common one that I'm about 95% certain you're going to see on your exam. And it's literally going to give you a Lineweaver-Burke plot, and they're going to say, what type of inhibitor do you have? So the way that I approach these is I say, okay, from my original to my inhibitor, my y-intercept increases. Y-intercept goes up. When y-intercept goes up, I know that that means that Vmax is decreasing. On the other hand, when we look at our x-axis, our x-intercept does not change. Therefore, Km does not change. Okay? So once again, drawing that formula, my absolute favorite formula, probably your least favorite by the end of this session. what we have here is Vmax is decreasing, but we're not affecting Km. So in my head, that's telling me that we're decreasing the concentration of both our enzyme substrate complex and our enzyme in equal proportions. And that's kind of the key here, because that means that it's a non-competitive inhibitor. And the answer to this is B. And since I got this from online and it gave the answer, we can also verify that this answer is B by doing that. And it is. So it is in fact a non-competitive inhibitor. Non-competitive. Okay. So, excuse me. So that's kind of the basic going through and how I figure out that it's non-competitive. From this graph, I look at Vmax, I look at Km. In other words, I look at y-intercept, and I would actually rather highlight this. I look at y-intercept, and I look at x-intercept. Are they changing? If so, how are they changing? Okay, how does that affect Vmax and Km? Which enzyme do I know does that? Right, that's my thought process going through this. That's actually, I finished a little bit early. That's all I have for you all, because I was trying to go through it a little quicker to give time for questions. But yeah, thank you all so much for coming. Good luck on your exam tomorrow. And if you need anything, come to drop-in tutoring. We're open till 8 p.m. today. Thank you all.